I'm live. Okay, so today we're going to be talking about Markov chain Monte Carlo. We will do stuff in the Stan language, although we're not going to get to the Stan Markov chain Monte Carlo algorithm today. We'll start that on Thursday, and even if not, we'd still have to go over the fact that this being Columbia having a lot of grants to develop Stan, me being paid by Columbia to develop Stan, me being paid by not Columbia to do stuff with Stan creates appearance of conflict of interest that you should all be aware of again. So going back to the multiple ways, potential ways, it actually turns out to be pretty much just one way to execute Bayes' rule. We have a problem that there's too few analytical solutions. There's a handful, but not with nearly enough generality. And the ones that can be done, like with the second problem on this homework, don't generalize barely at all to models that have multiple parameters. Now we haven't done a whole lot of those yet, or maybe any of those yet, because we've been limited in our ability to do these sorts of things. And particularly before there were computers, that's basically all you could do with Bayesian inference, was these sort of handful cases where you could get a somewhat analytical solution, but even then they couldn't evaluate special functions without a computer very well. So there was just really a handful of cases where you could legitimately say that you're using Bayes' rule. And when Fisher came along, was able to convince a lot of people in Britain that the Bayesian approach was wrong. But there weren't a whole lot of situations in which you could, without a computer, do maximum likelihood either. You had to restrict yourself to very simple models, like one parameter. And those were easier because all you had to do is take a derivative. You didn't have to do integrals. But it's still kind of hard to do maximum likelihood with multiple parameters, because you would have to solve a system of homogeneous equations, and that may not have an explicit solution, even if there is an implicit one. But anyway, Fisher was able to convince a lot of people that the objective approach to probability was the right way to go, and was somehow able to convince other people that the maximum likelihood thing was objective. Now, the fact that Britain unlost World War II with Bayes' rule, you would think would be a pretty substantial counter-argument to that. And for those of you who read about or saw the video from Sharon McGrain, goes into the history of this a lot. But basically, short version of it, this guy, Harold Jeffreys, who is a professor in geology, was basically the only person who was really willing to stand up and say Fisher was wrong. And Alan Turing was hanging around in the late 1930s, not particularly interested in geology, but would go to some of Jeffreys' lectures about statistics and statistical methodology and the Bayesian approach and whatever. So then the British got attacked during World War II. Turing got roped into not the army, but basically the intelligence, and trying to come up with ways to crack the encryption scheme that was used by the Germans to convey information to their submarines and also their planes and troops and stuff like that. Anyway, with the submarines, the British were basically in a really bad situation because it's an island, and the submarines had the whole western part of, like by Ireland and stuff, pretty much covered, and Britain doesn't produce enough food to feed its whole population, so it had to import food. And all the ships and stuff that the Americans were sending went like 2 miles an hour because they were loaded up with food and were basically easy targets for submarines. And they would just sink like every boat that they saw coming across. So they were running out of food, which is a fairly fundamental practical problem. But Turing was, developing this scheme to use Bayes' rule, and he had a lot of assistance with that. Women who joined the essentially counterintelligence thing. They didn't really have computers, but they had like hamster wheel things that could be turned that would crank out calculations, and they were fortunate enough that they were British or somebody were able to sink one of the German boats, and as it was sinking and on fire, 2 British military people or whatever swam into a sinking boat to dig out some partially decrypted messages that had been sent encrypted and then decrypted there on the boat. So they were able to get some information, and they were able to update their beliefs as to what encryption scheme the Germans were using based on the information that they had and other data that was coming in. And so then they got to where they could say with high posterior probability, this is what this encrypted message says when they intercepted those over the radio and Morse code and stuff like that, and we're able to say, okay, on the basis of these, what we think is the correct decryption of these messages, here are where the boats are, the submarines, and so they could send like counter boats and airplanes and stuff like that, and we're able to get more of the ships with food coming in to them. And so this was in like 1941, somewhere around there, and enabled Britain to last longer, and then eventually like D-Day and all that happened, and they started to turn the tide. But after World War II was over, Churchill was afraid that they were going to then have to fight the Soviet Union to drive them back out of Europe from the east side, and classified all the information as to what Turing had been up to. And Britain has like very strict secrecy laws and whatever, so no one was allowed to talk about this great accomplishment of Bayes' rule. As it turned out, like no one really had the guys to fight another war against the Soviet Union, so they just kind of gave them Eastern Europe pretty much. But anyway, they couldn't talk about it. And so we had this situation in which all of the real successes of Bayes' rule were by governments, mostly military. There was an episode where the United States lost one of its submarines with nuclear weapons, and I imagine Johnson was not too happy about that, and so they used Bayes' rule and eventually found the submarine. Things like that. But anyway, these were not, publicly known or even known to academic communities. So, lots of textbooks were being written on the frequentist method, and by the time you got to about 1970, it was possible to numerically solve optimization problems on computers without having to have like an explicit solution to the homogeneous system of equations. And at that time, there were a lot of people in the social sciences and elsewhere who really wanted to use empirical methods, and maximum likelihood in these frequentist things basically got a jump on everything, because in 1970 it wasn't really possible that we knew of to use Bayesian methods numerically on computers. It was actually also being done as part of the Manhattan Project in around 1950, but not only was that pretty secret, it was involving physics, and no non-physics person understood what was going on, even to the extent that they publish things. So it wasn't until like, 1980s or so where you could really do, numerical integration of kind of arbitrary functions, at least in one dimension, on a computer. And that was reasonably general, but it would only work, again, with models that have one, maybe two parameters, probably more just like one in. We could get away with two now. So that certainly wasn't as general as what could be done with frequentist methods at the time. Rubin sort of speculatively proposed this prior predictive matching thing that we've been using on the homework in 1984. Again, not that it was feasible to do, because computers were really slow back then. But even in theory, that's only going to work with discrete outcomes. And even if you have a discrete outcome, it's going to reject way too often when you have more than one data point to exactly match with it. And so we don't, the prior predictive matching was sort of good enough to get through one homework assignment, but it's not a general approach either. So, but it does suggest that, and what turned out to be the case, that we can basically substitute random draws for doing integrals that probably don't have an elementary solution in the first place. But again, we're really kind of limited to the univariate case. It's easy enough to draw from a standard uniform distribution. In a lot of cases, we can use the inverse CDF method to then change that draw from a standard uniform to a draw from some other distribution. There may be better algorithms in some cases, but the inverse CDF method, at least in theory, is really good, and then we can get independent draws of that. But it's hard to do the inverse CDF method in bivariate or multivariate situations, and in general, like basically the multivariate normal is one of the few, or transformations of the multivariate normal is one of the few multivariate distributions that we have an algorithm to draw from explicitly that would produce independent draws. So we want draws, but we want to be able to do it in general. And for that, starting around 1990, at least in like non-physics, non-military context, there was an article published in the Journal of American Statistical Association journal that showed how this Markov chain Monte Carlo idea could be used to by regular normal researchers to estimate stuff, to draw from a general multivariate distribution, in particular a posterior distribution, but we have to give up on the idea of having independent draws, and that presents some additional complications, but we want to start talking about this MCMC stuff today and then continue it on Thursday when we get to Stan. So I put this up before. This is the PDF for the bivariate normal distribution, and so this is one of the few multivariate distributions that we have an algorithm that we can draw explicitly and independently. And in the bivariate case, which is sort of sufficient to illustrate the intuition, it's because we can rewrite the bivariate normal PDF as the product of a marginal normal for x and a conditional normal for y given x, where the conditional expectation for y given x is in red. Here it's shifted over by this amount, where beta is rho times the reciprocal, or the ratio of the standard deviations. And then the conditional standard deviation is in blue here. It's the marginal standard deviation of y downscaled by 1 minus rho squared. And so we can get draws, independent draws from a bivariate normal distribution by drawing from a normal distribution marginally for x, using that realization, conditioning on it, drawing from the conditional normal distribution of y given x, and those together are one draw from the bivariate normal distribution, and we can do that as many times as we want to accumulate up a bunch of draws. And so we're going to use the example of a bivariate normal to illustrate these Markov chain Monte Carlo schemes, because we basically know how to do this with independent draws, and then to see if Markov chain Monte Carlo scheme, which produces dependent draws, is going to be able to sort of adequately mimic this well enough. And just to remind ourselves, we have this thing. Where's my x? There's my x. Is sort of pseudo 3D representation of the bivariate normal PDF that looks like this. And so if you look at it along exactly along any axis, it looks like a normal margin. That's true for x. It's also true for y. And that's because the margins of a bivariate normal are also univariate normal. Okay, so I'm going to put up Stan syntax for this. No particular, well, there is a reason, but it could have just as easily been done in R or Python or another language, but this just gives us another opportunity to get a little bit of exposure to the Stan language, even though we're not yet talking about the Stan algorithm. So this is essentially the same way that you would define a function in R. It's just using the Stan syntax. And so when you write one of these functions, one, you have to put it in a functions block. This one is called binormal_rng.stan, and it's on Canvas. So the first thing you have to do is say, what sort of object is being returned by this function. In this case, it's going to be a matrix that has two columns for the x and the y coordinate. Then we have the name of the function. This is binormal. Any function that draws from random numbers has to end in a _rng postfix so that Stan knows how to treat that. So this is going to take an integer argument, s, for the number of draws that we want from this bivariate normal. And then we have real values, which are scalars, for each of the 5 arguments or parameters to the bivariate normal. The marginal expectation of x, marginal expectation of y, marginal standard deviation of x, marginal standard deviation of y, and the correlation between those two. So this is kind of like defining an R function with the additional complication that you have to specify what is the nature of each of these arguments, because it's going to get translated into C++ and compiled, in which case, in order for it to allocate the memory and do stuff that it does in C++, it has to know the types of these things before the function is called. Unlike R, where it can sort of figure out what it needs to do at the time that you call the function in terms of like processing the arguments and stuff like that. So first thing we're going to do on the inside of the body of this function is to allocate a matrix with s rows and 2 columns to hold these draws from the bivariate normal distribution. Then we're going to define 2 constants, which are the beta and the sigma from the conditional distribution of y given x. Those can be done outside the loop over s because they are not changing as a result of realizations of x or y or anything. They're just constants. And so then we loop from s up to big S to fill in our matrix of draws. So inside the for loop, we're going to allocate 2 more local variables, x and y, which are real numbers. So we draw from the marginal normal distribution with marginal expectation mu and marginal standard deviation sigma, get that realization of x, and then use that realization of x when we call normal RNG again to draw y from the conditional normal distribution, which has this conditional expectation and conditional standard deviation sigma that we calculated outside the loop. So draw x from the margin, draw y from the conditional distribution given x. So we have to calculate each time we get a new x, the difference between x and its marginal expectation. And so then we just stuff x and y into the first and second columns of the matrix draws, and then when the loops are all done, we return draws to the outside of the function. And that is about it with that. We can call expose stan functions. This file, again, is called binormal_rng.stan. and this will translate it into C++, compile to C++, and make this function available in R's global environment. So then we can just specify some of these constants. In particular, rho is 0.75, and we can draw 26 times, because that's all I could fit on a slide, from this binormal function and calculate the column means. So we're now sort of estimating mu x and mu y on the basis of these s being 1,000 random draws. And so we'd sort of put some row names and column names on that, and I will show the result of that in the next slide after we talk about some stuff with Markov processes. So a Markov process is a sequence of random variables. And it has a very particular dependent structure where everything in the future realization of the sequence is conditionally independent from everything in the past of this sequence, given what is happening in the present. So the way you can think about it is, tomorrow is independent of yesterday, conditional on today. But marginally, nothing is independent. And that allows us to use Markov processes in a variety of ways because they can have a pretty rich dynamic structure. We already saw one example last time of an autoregressive model of order 1. That is a Markov process that happens to be linear. But in general, when we're talking about Markov processes, the dynamics of them may be nonlinear. So if we think of some random variable in a sequence indexed by little s, and we say the random variable x sub s has some conditional PDF that, so this should probably be an x right here. That should be x, little x sub s. And we only have to condition on the previous realization of that sequence, given that all the ones from last week don't matter as far as affecting the PDF for the S1 today. And if we have a whole sequence of those, then we get some joint PDF over all S of those, which can be written as some marginal density for the 0th one that kicks off the sequence, and then from little s to 1 up to big S, multiplied by the conditional PDF for today's x given yesterday's x. And that sequence can go as far as we want in the future. And then the question for Bayesian estimation, is it possible to construct a sequence, basically to choose these distributions for all of these things, such that the marginal distribution of the last element in the sequence has the distribution that we want, at least as the number of steps in the sequence gets large? Does it converge in distribution to a distribution we might want to specify, such as a posterior distribution, or in this case, such as a bivariate normal distribution? And the answer to that question is yes. There are a variety of ways to do so. Only a few are used in the Bayesian context, and really you're only going to need Stan. But in general, there are ways to construct the transitions of this Markov process such that the last element of the sequence is converging to the distribution that you want to draw from. And basically, once it gets close to the target distribution that you're trying to draw from, the subsequent iterations of the sequence all stay close to that target distribution. And so basically, the idea of using this for Bayesian analysis is to run one of these Markov processes long enough until it gets close enough to the posterior distribution we're trying to draw from, and then keep 1,000, 1,000,000, whatever draws realizations of this Markov sequence after that, and those will be a collection of draws, at least approximately, from the posterior distribution that we want draws from, but they won't be independent of each other. So they have the right marginal distribution, but they're not independent. And we can see the consequences of that as we go along. So one of the first algorithms for doing this Markov chain Monte Carlo is used in the Manhattan Project, which involved Metropolis and Teller and the other Teller's wife, and a couple others, Ariana Rosenbluth, and her husband, whose first name escapes me, but was probably also named Rosenbluth, came up with this. It's not, they kind of collectively co-authored most of the papers, so it's not entirely clear who came up with what parts of it. But anyway, suppose you want to draw from some distribution whose PDF is given. You don't have a customized algorithm to do so. You can initialize your parameters to some legitimate value in the parameter space, and then repeat the following step a whole bunch of times. Draw a proposal from some distribution whose PDF is easy to evaluate, Q. This could be your prior distribution. It doesn't have to be. Basically, some distribution whose PDF is easy to evaluate and is defined on the same parameter space as theta being drawn from. And then we calculate alpha star. So this alpha has nothing to do with the alpha on the homework. This is what's known as the acceptance ratio, which is the minimum between 1 and this product of 4 terms here. So the PDF evaluated at the proposal of theta divided by the PDF evaluated at the previous version of theta in the sequence, and then multiplied by the PDF of the Q distribution evaluated at the previous element in the sequence, and then divided by the PDF of the Q distribution evaluated at the next proposal in the sequence. And you might say, well, the problem with all these PDFs is that we don't know how to evaluate their denominators. Like, technically those involve integrals. However, as you can see, if we divide f, by f, whatever constants are going to cancel. So we don't actually have to use the whole PDF. We just have to use the kernel of the PDF, the part that involves theta, and that is often going to be an elementary function. Same deal with Q. And so they have, Metropolis and later Hastings, that generalized this with the Q stuff, overcame the problem of we have these unknown constants in the denominator that involve intractable integrals by using ratios such that all those constants cancel. And so that allows us to compute alpha star, which will be some number between 0 and 1. And then third step, if alpha star is greater than a realization from a standard uniform distribution, set the current value of theta equal to the proposed value of theta. If not, keep the old value of theta for another step in the process. Don't update it to theta prime. And then store this realization of theta as the sth draw of the process, and do that over and over again.
Don't really understand why constants cancel with a ratio.
Right, so imagine there's some constant that involves an integral that you don't want to cancel, or that you don't want to evaluate in the denominator of f. It's the same function being evaluated when you divide by f of theta. So let's say f is the beta distribution, just to be concrete about it, and it has that beta function in the denominator, which, like a long time ago, you wouldn't have had computers to evaluate accurately. So that beta alpha, or beta AB, is the same here as it is there. So the beta AB part, the special function, those values are going to cancel, provided they're not like both 0 or infinity or something like that. And so you only need the kernel of the beta function in order to evaluate this, and also whatever your Q distribution is you only need the kernel. You don't need the normalizing constants.
Okay.
Did I draw that up? So let's say f is the beta distribution. So we have f of theta prime is going to be theta prime to the a minus 1, theta 1 minus theta prime to the b minus 1 divided by question mark, where question mark is the beta function at a, b. And then we're going to have f of theta theta to the a minus 1, 1 minus theta to the b minus 1.
Okay.
And so if we divide that, whatever was the question mark, whether we can evaluate it explicitly or accurately or not, cancels, and we just have the kernels. So they evaded the need to constants by canceling.
Just one substitute. Do we know it's not zero and infinity?
How do I know it's not? These are valid PDFs,
Okay.
so they integrate to 1, and so they need.
I just like, how is that legit? Like, you know, so basically, what does the once we put this in the denominator, what does it represent? That fraction represents nothing, or?
So individually, these don't represent anything. Together, they calculate alpha star, and alpha star is your acceptance probability for theta prime. So, you know, kind of like we have with partial predictive matching, we have this criteria to decide whether to keep the match. Here, alpha star is our criteria, and we want to accept theta prime with probability alpha star. But it doesn't have a substantive interpretation.
Having a lot of problems because it's the marginal which is the problem all the time. Okay, so it's always the denominator which is going to be an issue for us, like never the numerator.
Right.
Okay.
Specifically, never the kernel. Like you could cancel the constants in the numerator as well. So the important thing are the terms of f that involve the random variable in question. Anything else constant, no matter how complicated it is going to cancel by division. Okay. So, you know, and the original Metropolis, it just assumed that the Q ratio was going to be equal to 1, in which case you don't actually need it. So this is a little bit small, but how would we do Metropolis-Hastings from R using functions defined in the Stan language? So we're going to need the bivariate normal PDF, or in this case, the log PDF. That's our f function that we're going to have to evaluate the ratio of. In the case of a normal distribution, like in the denominator, it just has like 2 pi and stuff like that. So these are all explicit. We actually wouldn't have to drop the constants, but they cancel whether we can calculate them or not. Okay, and this function, it's going to have as its first argument x and y together in a row vector of size 2, and then the other 5 arguments to the bivariate normal density function. This is going to return a scalar real number. So again, I calculate my beta and I calculate my sigma for the conditional normal distribution of y given x. And then I want to return, since this is the log PDF rather than the PDF, I want to return the sum of the logarithms of the normal distribution. So we have marginal normal distribution for x in log PDF form plus conditional distribution normal for y given x, and so we're going to use the conditional expectation and the conditional standard deviation there. And it's going to return back this one scalar number, which is the sum of those two log PDFs. Then we get to the function that actually uses the Metropolis algorithm to draw from this bivariate normal distribution using this, or this is the log of f. So this is going to return a matrix with 2 columns. Takes the number of draws we want to do. This half-width thing, which pertains to Q, I'll explain that in a second. And again, all the arguments to the bivariate normal density function. So allocate our matrix to hold the draws. Initialize x and y to 0. Those can be anything as long as they're real numbers. And then we loop from 1 to big S. So here I'm going to use the uniform distribution as my Q distribution. Like I said, this can be anything that's easy. And I want to draw my proposal for x from a uniform distribution whose lower bound is x minus something and whose upper bound is x plus something. So I get this like interval uniform to draw my proposal for x from, and I can use the current value of x as the center of that interval. So just some half-width in either direction along the x. And so I draw my x proposal. I do the same thing to draw my y proposal. I then calculate alpha star by evaluating my bivariate normal log PDF function at the proposal, so x underscore and y underscore with like all its arguments. And then I subtract, which is to say, well, I'm doing this in logarithms. So I subtract the logarithm of the bivariate normal evaluated at my old values of x and y, and then I exp that difference in order to get something that's not on the log scale, that's on the PDF scale. And then, okay, that has, technically it's the minimum of 1 in that thing. But when I take my uniform draw from the standard uniform distribution, if alpha star is greater than that, then we're going to accept it. And if alpha star turns out to be greater than 1, like that's fine. It just means we're guaranteed to accept that draw. The fact that I'm using the uniform distribution as my Q means I'm in Metropolis territory. That's always going to be 1, so I don't have to multiply by that. Anyway, if this criterion is satisfied, I change x to x underscore and I change y to y underscore, and then irrespective of whether that happens or not, I stick x and y in the sth row of my matrix of draws, and then after all the loops are done, I return the matrix of draws again. However, if this criterion is not satisfied, which is to say my realization from the uniform distribution is less than alpha star, then I'm going to continue to use the same x and y on the sth row of my matrix that I used at the previous step. So it's the same x and y again. And that is, it seems like that's weird, but that's necessary in order for this algorithm to work. Anyway, I can expose it to R, and I can call it a whole bunch of times using 2.75 as the half width. I'll tell you why in a second. So if I look at the means of the draws of x and y that come from the Metropolis algorithm across the 26 times that I do it, you see that they're all like kind of close to 0, which makes sense because my mu x and mu y were exactly 0. They could be whatever I want. And okay, so all of these are kind of in the vicinity of 0 when you take the average over S is 1,000. Yeah, 1,000 draws. So, okay, so we got these. And then if we compare it to the same thing, but involving the independent draws from the function that we defined before, binormal RNG, in that case, we only took 100 draws rather than 1,000. And we can see we get estimates of the average, which again are in the vicinity of 0. but they're not exactly zero because we're taking a finite number of draws. But you might notice that these draws, which there were 1,000 dependent draws from a Metropolis scheme, are about as accurate for estimating the mean of X and the mean of Y as 100 independent draws. And that's kind of the downside of using these MCMC schemes. They're very general, but the draws are not independent of each other. So they're less efficient for estimating the means and the other things that we might want to estimate than would independent draws from that distribution if we could obtain independent draws from that distribution. But in general, with these multivariate posterior distributions, like condition on data, they don't have names, they don't have special algorithms to draw with them. And so we're limited to what can we do with dependent draws. And thus our efficiency is a bit less, and maybe a lot less. But that's kind of the price to be paid for having a scheme that can draw from, basically any multivariate distribution with great generality. Question?
So we're doing this because we want to estimate the parameters, like the and the mu x, like in the replicate. These are the things that we set at the beginning, or is that the thing we're looking for? I'm a bit confused by what.
We set it at the beginning, so we know that it's set to 0, and then we're seeing how well can we estimate a 0 from all these draws that are ostensibly being taken from a bivariate normal distribution. And so if we just have like 100 draws, okay, we can estimate it like kind of okay, as long as those draws are independent of each other. If the draws are not independent of each other, we need more of them in order to get about the same amount of accuracy in estimating those zeros.
But when we're going to work with like things that when we don't know the parameters, we're going to write the same thing, but not specifying the mu x and everything, and just like getting them through simulations. Okay, so the function here works even if we don't know the mu x or whatever. Okay.
Correct.
Yeah.
Yes.
All good. From the previous slide, for each s, even if we're not updating theta, right? So it's like, say we don't meet the alpha and we're not updating theta, we're still storing x and y.
Yes.
Isn't there still a stochastic component to x and y even if theta remains the same? So x and y.
Marginally, yes.
Okay.
So before we even start, the x and the y, they all have the same limiting distribution. It's just conditional on what's happened before. They don't change from s to s minus y.
Okay.
Okay. So we got some of that. So perhaps a better way to illustrate this, what we've been asking about here. Here I'm just going to take one set of 1,000 from the Metropolis, not like 26. So first of all, if you look at the number of unique rows of x and y, it's only 236. And there's 1,000 rows total. So 236 times it changed, and 764 times it didn't change. It kept the same x and y as the previous. And if I plot this as a time series, you can see it has these flat spots in it where, 1 or 2 or 3, it kept the same x and y that it had in the previous one as the next iteration. And so this thing kind of hops around in a non-smooth fashion, and then sometimes you get unlucky and maybe 8 in a row it doesn't change. That's for x. Similar thing for y. So anyway, this is not like a smooth random walk or something like that might be a little bit easier to analyze because of the duplication. But like a random walk or a AR1 process, all of these things are marginally dependent on all the others. But it is the case that like the last one is basically independent of the first one. Not totally, but for all intents and purposes, the ones way late in the process are essentially independent of the ones way early.
That was like way better than it could have been though. So maybe I'm just like not able to see this right, but the X's and Y's, if it keeps the same X, is it also keeping the same Y?
Yes.
Okay. That's what I thought, but it looked like some of those were.
Yeah. Anyway, more evident from the code.
Yeah.
So either X and Y get updated together or they don't.
Okay, thank you.
Okay, so we got that. All right, next idea, and this is actually probably the most important slide because we're only going to spend like part of a day on Metropolis and Gibbs. They were very important historically, but we don't want to actually be using them going forward. But the idea of effective sample size is one that we're going to keep harping on for the rest of the semester. So if a Markov chain mixes fast enough, and I'm not going to define mixing, but basically that these ups and downs are like rapid enough and there's no real pattern to them and things like that. That pertains to the mixing. So if the Markov chain is mixing fast enough for the Markov chain Monte Carlo central limit theorem to hold, then we can define the effective sample size as S, which is the nominal number of draws, 1,000 in this case, divided in the denominator by 1 plus 2 times the infinite sum of the kth order autocorrelations, where rho sub k is the ex ante autocorrelation between realizations of the Markov process that are k steps apart. So in order for this to be like useful at all, this infinite sum has to converge to something. If it diverges to infinity, then we're going to have S divided by infinity, and our effective sample size would be 0. So we're going to need these kth order autocorrelations to eventually get close to 0 in order for this summation to have a limit. But assuming that that process does have a limit, then the Markov chain Monte Carlo standard error for estimating the mean from S dependent draws is equal to the true standard deviation of the process, which we don't know, but we're trying to estimate, divided by the square root of the effective sample size. And this is a very similar concept to those of you who might be familiar with like survey sampling techniques. When someone does a poll, they don't actually do simple random sampling from the population. They're going to do like cluster random sampling or a variety of other schemes that are cheaper to implement for the pollster company, but create some dependence. And so if you look at like the footnotes of a poll, it will say, we called 1,000 people or whatever, but there's a design effect that has to be estimated, which basically says like, given the fact that we didn't actually do like independent random sampling from the population, we did something cheaper. The effective number of people in the sample is less than the nominal number of people in the sample for the purpose of estimating, the proportion who favors Sanders or Bloomberg or, whatever that might be. So if all these autocorrelations were 0, which they're not, then the effective sample size would be equal to the nominal sample size, and that would be fine. You can think of, in general, irrespective of what the rows are, and they have to be estimated as well, you can think of the effective sample size as the value of your dependent draws collectively. Or not the value, the worth of the dependent draws collectively. So if our effective sample size is like 100 and our nominal sample size is 1,000, what we're saying, like we did in this situation, that we get the same accuracy in estimating the mean from 1,000 dependent draws as we would in expectation from 100 independent draws if our effective sample size is 100. And so you want these effective sample sizes to be, as close as you can to the nominal sample sizes. But with things like Metropolis-Hastings, they can be considerably less. 100 would be like fine in this case, but this is still a really simple example in the grand scheme of things. With more complicated models, you could easily get effective sample size of Metropolis-Hastings that is much less than 1/10 of the nominal sample size. Anyway, all of this has to be estimated, and if the effective sample size is really low, the estimator of the effective sample size is not particularly reliable. But anyway, in this case, it was decent, good enough, and that we got an effective sample size of about 100 for both the X and the Y margins. And so if you only needed like 1 decimal place of accuracy, probably 100 independent draws would do it, or 1,000 dependent draws, in expectation would be worth the same amount as 100 independent draws. Question?
So I'm a bit confused because we need the to know the standard deviation to know the effective sample, but we're doing MCMC to know the standard deviation. So isn't like a big of a loop what we're doing?
So we have to estimate the sigma and we have to estimate the rows, but it's not circular. It's just we don't know these exact numbers, and so we have to estimate them, and our estimators are not perfect for a finite number of draws, etc. But these are all computable under the assumption that the Markov chain Monte Carlo central limit theorem holds, and that's not something that you're really going to know in advance. You kind of just have to hope. There was a question on Campus Wire today about that. So in some cases, it's been proven for some posterior distributions that the Markov chain Monte Carlo theorem does hold, in which case like these estimators of the effective sample size make sense. But those are not very general proofs. They're very specific to particular types of models. So if you're not estimating one of those models, you're estimating something else where you don't have a proof that this is going to hold. You basically, what you're left to do is try to get a Markov chain that mixes as fast as possible, which is Stan, and then in the output try to assess whether it's mixing fast enough for this to hold. But that is something that is kind of Stan specific, and so we'll talk about that on Thursday. Now the next one, Gibbs samplers have had even more of an impact on Bayesian analysis. This was basically that 1990 paper by Adrian Smith and Gelfand talked about the Gibbs sampler sort of for the first time to statistician audiences. And you can think about a Gibbs sampler as a special case of Metropolis-Hastings where the Q distribution that you're drawing the proposals from is equal to the so-called full conditional distribution derived from the posterior distribution that you're trying to draw from. So what is a full conditional distribution? It is the conditional distribution of the kth parameter conditional on all the parameters but the kth parameter. So in sort of our syntax, negative k means exclude the kth parameter. So this is the conditional distribution of the kth parameter given all of the other parameters. And it can be shown that if you use this Q as your proposal distribution, alpha star is going to be equal to 1. And so all of your proposals are going to get accepted. There's no repetition of draws from the previous iteration into the next one. And you might say, okay, that's going to be better because we're not going to have this plateaus in our time series plot. However, it's not that great because the conditional distribution may produce proposal draws that are very close to the draw of the k theta on the previous iteration. Not exactly equal, but they can be sort of arbitrarily similar. If the conditional variance of the full conditional distribution gets close to 0. And so they're a little bit different, but they may not be so different. And if they're pretty similar, then the dependence is going to be high. The Markov chain Monte Carlo central limit theorem may not hold. Even if it does hold, the effective sample size may be disappointing, and it's not super great. But anyway, you can loop over all k parameters that you have to draw sequentially from each full conditional distribution, assuming you can work out what that is and you have an algorithm that will enable you to draw from that distribution. And so, different people have worked out like what combinations of priors and likelihoods yield full conditional distributions whose kernel is, recognizable in an explicit form, like this is a gamma kernel, in which case you use the gamma distribution to draw the proposal for theta k. And then, the next distribution in your full conditionals may be a beta distribution. And so you use a beta distribution for that. So anyway, as long as you have algorithms to draw from each full conditional distribution, this can be okay. But for a lot of models, really most of them, there's going to be some parameters for which the full conditional distribution is not one that is recognizable as like a famous distribution. And so you don't have an explicit algorithm to draw from that distribution. And so you might have to do something with like an inverse CDF that's not elementary or something like that. Do something else in order to obtain a draw for that kth element of your theta vector, and then move on to the next one. So, question.
I have two questions about alpha with a star. One, so why exactly are we the matching algorithm that we have to replace the theta that we actually have with our made-up theta says that we replace it when it's larger than 1. But wouldn't we want it to be exactly 1? Because,
so in the Metropolis step from before, we accept if alpha star is greater than a draw from the standard uniform.
Okay.
And so if alpha star is greater than 1, then we accept it irrespective of what that draw from the standard uniform is. In the case of Gibbs, which can be seen as a special case of Metropolis, the alpha star is always going to be 1. So irrespective of what the draw from the standard uniform is, it's going to be less than alpha star, in which case we accept. And so because that's the case, we don't actually have to mess around with the draws from the standard uniform when we do Gibbs.
Okay, and then second question is, okay, so we have, at least in the previous example, so we have the matching algorithm, and that brings us to the problem of independence. But since we are doing that in order to cancel out the terms which are constants, why don't we just ignore them from the beginning and then integrate instead?
Ignore them from the beginning because we know that they cancel, but it's not feasible to do numerical integration, like in the case of Metropolis, over big or even medium-sized multi-dimensional parameter spaces. We probably could do it with just 2 dimensions. But if we want an algorithm that works with 3 parameters, 4 parameters, 5 parameters, doing numerical integration over that whole thing simultaneously is not something that we can do accurately if we limit ourselves to deterministic algorithms. Essentially what all these MCMC schemes are doing are calculating definite integrals stochastically with a big sequence of random draws rather than a deterministic approach like the integrate function in R, which just works with 1 parameter. So how would we do Gibbs sampling from the bivariate normal? So this is same sort of setup before. We're going to turn a matrix with 2 columns. It has S rows for each of our draws. So we're going to initialize X to something. That needs to be outside the loop. We're going to calculate the constants that we need. In this case, we have to calculate the conditional standard deviation of Y. It's different than the conditional standard deviation of X. But anyway, calculate all these constants, go into our loop, and we draw a realization of Y from the conditional normal full conditional distribution of Y given X. So mu Y plus beta times the quantity X minus mu X, and using sigma YX as the conditional standard deviation. Okay, take that realization of Y, turn around and draw X from the conditional normal distribution of X given Y. So that is going to be flipped around. It's the same idea, but things are switched around for the conditional distribution of X given Y. We have Y minus mu Y, and we're using as the conditional standard deviation sigma XY. And then we don't have to worry about the acceptance because that's guaranteed. We just put X into the first column, Y into the second column, and then go on to the next iteration of the loop. So in the Gibbs thing, we draw Y from a conditional distribution, then X from a conditional distribution, then Y from a conditional distribution, then X from a conditional distribution, over and over and over again. And that is similar, but crucially different from the algorithm that we talked about at the beginning, where we could get independent draws from a bivariate normal by taking X from its marginal distribution, Y from the conditional. X from the marginal, Y from the conditional. X from the marginal, Y from the conditional. That produces rows of draws that are independent of each other. What Gibbs is doing, which is asymptotically equivalent, but for any finite S, it's going to be a little bit different due to the dependence, is conditional, 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 instead of marginal conditional, marginal conditional, marginal conditional. And this leads to draws that have more dependence across the rows, less effective sample size than an equivalent number of independent draws from this bivariate normal distribution. Anyway, we call Gibbs RNG one time after exporting it to R, and we get plots that if you visually just compare them to the one for Metropolis, it seems as if the Gibbs in this case is mixing faster, and it is. There's no plateaus in it because it's going to change at least a little bit every time. And in this case, if you estimated it out, you would get an effective sample size of about 300 on a nominal sample size of 1,000. And so in this case, it's like 3 times more efficient than Metropolis at estimating these means of X and Y, but only about less than a third as efficient as if we had independent draws, which we can in this case because it's normal, but for an arbitrary posterior distribution, we're just never going to be able to have independent draws. So all we can do is get dependent draws and then hope the central limit theorem holds, and then estimate the effective sample size. Questions about Gibbs? Or whatever? Anything? No? Yeah.
Try to use an intuitive analogy. Bear with me if it's a little bit silly, but with the Gibbs sampler, it's we're deciding whether to take steps, and here it's we're okay doing very small steps. Whereas with the previous one, it's we might be taking larger steps, but we might not be taking them each time if we're not reaching the alpha. Is that fair?
Yeah, that actually does make sense, and I forgot to say what I promised I would say. The 2.75 thing, which was what I passed to the half-width argument of my Metropolis, I chose that 2.75 in order to achieve an acceptance rate of about 23, 24%. That is very close to the optimal value for maximizing effective sample size. And so the trade-off that you alluded to, so sometimes, a lot of time, 3/4 of the time really, you're gonna stay in the same place, and that intuitively seems like it's gonna create a lot of dependence, and then lower effective sample size. But there's roughly a 1 in 4 chance that you make a relatively big jump, which is going to diminish the dependence, increase the effective sample size. And so for very simple cases, we can calculate the optimal acceptance ratio. And in this one, it's about 23%. So I fiddled around with my half-width in order to achieve it. But optimal can still be, like, it's optimal among Metropolis-Hastings. It's still not great. We're only getting like 100 effective on 1,000 nominal. And at least visually, and also if you calculate the effective sample size estimate, seems a lot worse in this case than doing Gibbs, which never sticks, but how much of a big jump you get depends on, in this case, basically how big rho is. If rho is close to 1, then the conditional standard deviations are going to be close to 0. And so my jumps are going to be not far away from the conditional means. And it would be more slower mixing. Okay. So the kind of the issue with Gibbs is, in addition, like, it can be kind of slow mixing, but also you have to be able to work out what these full conditional distributions are, and you have to have algorithms that draw from those full conditional distributions. So if your algorithm, or if you're, you do the figuring out what the full conditional distribution is from the joint posterior distribution that you implied with your kernel of base rule, and it turns out to be like some of the full conditionals are normal and some of them are gamma, then it's okay, because we have like R gamma, R norm to draw from those distributions in R in almost any other language. But what do you do when the full conditional distribution doesn't have a name and it doesn't have an algorithm? Well, you need some fallback way to sort of draw from a distribution that works in general, irrespective of whether the distribution has a name. And there's a package called R-Uniron, which basically approximates the inverse CDF. I don't think it's that great, but in principle, it's a good idea. It approximates the inverse CDF of an arbitrary distribution if you give it the log kernel. And so if we had at least a good approximation of the inverse CDF, we could draw from a standard uniform, stick that draw of the standard uniform into the approximate inverse CDF, and approximately get a draw from the kth full conditional distribution, and then we wouldn't have to rely on constructing a posterior distribution whose full conditionals are in known forms. And this is essentially what the Bugs family of software did. Very important, starting around 1995. Bugs software was released for Unix, so not that many people were capable of using it. But in 2000 or 2001, they came out with a Windows version. This is back when everyone was using Windows. And so that was an important step forward for people being able to use Bayesian things. Nowadays, Bugs has been mostly superseded by something called JAGS, which is a similar algorithm, but it's written in a different language, C++, whereas the original Bugs and WinBugs were written in component Pascal. And there's only like 2 people in the world left who know how to program in component Pascal. There's also something called OpenBugs, but it is not as good as JAGS and not being actively developed anymore. Anyway, here is a function which I call bugs-ish, which is basically just a pure R function that I can write on one slide that hopefully gives you the intuition for what Bugs was doing. Bugs was actually a little bit more clever than this, and the approximations were better, but this gives a sense of the algorithm. So you just initialize your matrix of draws, you loop from S, and then inside the loop over S, you loop from the first parameter to the kth parameter. Inside the loop, you define a full conditional distribution, which just depends on a scalar value, theta k, and you take the old values of theta, up to k minus 1, and the old values of theta from k, big K subtracted to little k, and you just put your proposed value of theta k in the middle here. And then you call these functions that are in the R Uniron package to approximately draw from this full conditional distribution that you defined, and you get a new realization of theta k, and you go on to the next k. And then that loop finishes, and then you go in the outer loop, each time stuffing the whole value of theta into the sth draw of draws, and then that returns. So anyway, don't get too hung up on this. Definitely do not use this function. It's worse than Bugs, but you should also not use Bugs because it's worse than Stan. But the thing about Bugs in this approximation of what Bugs does is that it would have enabled us to use Gibbs sampling even if we didn't know explicitly what these full conditional distributions are. They happen to be normal, and that happens to be easy. So that would have been better. But if we didn't know, or if they weren't normal, or any other thing that we recognized, we could do the Bugs-ish, or the Bugs actual approach. So you call that. It goes real slow. And you can see its mixing is not quite as good as the mixing from the actual Gibbs sampler on a bivariate normal. It's decent, got an effective sample size of about 200, but less than 300, more than 100, which is what I think we got for Metropolis. Where was that? Yeah, about 100. So anyway, in this case, which is a very easy one in the grand scheme of things, Metropolis got an effective sample size of 100. Actual Gibbs sampler got an effective sample size of 300. Imitation Gibbs sampler that's had some approximations and stuff had an effective sample size of about 200. And then the question that we're going to take up on Thursday is, could we get something that is as good or better from the MCMC algorithm in Stan, which is much more modern, and or would the algorithm in Stan allow us to have it work in a richer generality of classes? And so basically what we're going to see on Thursday is that the algorithm in Stan requires you to put in the same amount of effort to figure out what the kernel of your posterior distribution is. So something like this to evaluate the log PDF of your posterior kernel. So it's the same amount of effort as Metropolis. You don't have to derive any full conditional distributions or things like that. But you get the effective sample size that's about as good as Gibbs can be, and oftentimes a lot better. So there's no analytical derivations of full conditional distributions or anything like that, but you still get the good effective sample size. And when you don't get the good effective sample size, Stan will give you a lot of warnings, which are not really available if you take the Gibbs approach. So we'll see more about that on Thursday. We'll also talk about the answers to the homework on Thursday. So if you have more questions about that, be sure to put them on CampusWire. Okay, so see you then.